This says exam 2 review. So here's some of the list of questions. I don't know if I've ever asked a deflection problem, so I don't think I'm going to start. But there was deflection was that was from channel 4, chapter 4, being collected on here. So it is up for grabs, but spoiler alert, I don't think I'm asking that because it makes the exams too long. There's also buckling. So here's a buckling problem. I think I have asked a buckling problem before, so I think reviewing it and if I did, it was probably be for a buckling problem, what I would ask, or what I would be looking for was that you at least checked to see if it was slender or not, considered Johnson or Euler, and then use the one that was the correct one for them. End conditions can often be a point of contention or a difficult thing to try to decide. So there's a couple things on a buckling problem that I would be looking for was that you, first off, that you checked these things and then that you got them correct. And then the nicety is to get the correct answer to predict what the buckling load would be. So we could look at one of those, although it's when I write an exam, a lot of times I will, let me take that back, I will always, I have a couple times not done it and made a mistake, I will always take it and time myself so that what happened in Thermo 2, don't say this on tape, doesn't happen, right? that you unintentionally make the thing extremely long. I've accidentally I thought, okay, yeah, this problem, that should be plenty of time. They got plenty of time for that. And then had that nobody finished and not even got close. Okay, so I will take it. So I will write a buckling problem and a couple other problems, and then take it and then go, that's way too long, and then I'll scratch one. And if I'm going to scratch one, it'll be the buckling problem. So I'm not telegraphing that there won't be a buckling problem. I'm just telling you, here's some information that I would probably work on a couple just to be familiar with it, but I wouldn't put a whole lot of time into a buckling problem. It's an important thing, but for all around, but it's not as important to mechanicals as it is to civil. Here is a general problem. I think I actually had this as a homework problem, but it's still, will be worth trying to go through. I may or may not ask a problem that's a door handle problem. So this isn't really a door handle problem where you would really need to do an FBD, but I really want to measure your ability to get the loads and the distances in the right configuration and in the right frames, and then be able to solve them. FBD is very important to me that you be able to get it all sorted out. Because I have found when asking one on a final exam, so if I don't ask it on this exam, it will be on the final exam, and it always kills me when people can't get it right. They could just flub it up because this is an exam, but they might not be able to do it, which is troubling to me, right? So, letting you know, this is a good problem to try out. This is too hard of a problem to try out, but it seemed like a neat idea at the time. But it's worth going through to work through a difficult problem. But here is one where it has a little bit of a thing. And I think this was actually an exam problem, but at Coast Guard, but it might have been a take-home problem. But I came up with one with real numbers from the gearbox. But I put the helical gears in there instead, so I'd have an axial load, which isn't something you've experienced yet. So that's sort of a jerk move to do. But it was a problem. A stress concentration problem. This is okay. So the combined stress concentration problem, right in there. And what did I ask? Can this arm support this loading without failure? So this is because it was brittle. You should know that you need to use brittle Coulomb more, right? Didn't ask for brittle Coulomb more. You should check for brittle Coulomb more, telegraphed within the problem. Pressure vessel problem, a little bit too easy. This is a straightforward pressure vessel problem. I probably, when asking a pressure vessel problem, would put a twist on it, almost literally put a twist on it. There's a pun. Unintentional puns are the best puns. Fracture mechanics problems, I am not asking a fracture mechanics problem. So you do not have a homework problem for fracture mechanics. I will not ask a fractional mechanics problem. Here's a cantilever problem. So this is actually, believe it or not, that's a door handle problem. But it wouldn't look like a door handle problem. It looks like a gear problem, but it's a door handle problem. The door handles are really, is my short, what I'm calling cantilever beam problems. So worth looking out. And you want to find the worst case scenario. So even though it's simple, it might be worth doing an FBD. I got to tell you, let me point this out. I have a couple times already broken my own rule about making FBDs. That you can get the equivalent loads, the moments, without an FBD. You can do it. But only do it when you can do it. If that makes any sense. Don't skip it. Don't skip the FBD and then get the wrong answer. Got me? Yeah. You skip the FBD and you get the wrong answer, big points. Well, but I don't do that anymore. I don't do the minus this and minus that and minus that. I'm an English teacher grader now. I go X, 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 take a step back, look at the thing. This was 60% successful. No, for you guys, 90% successful. Somewhere in that range, right in there. I don't like half points anymore. So, but it'll all work out in the wash. It all works out in the wash. But if I see no F, you get the wrong reactions or wrong equivalent loads, either way you want to look at it, and you didn't do an FBD, that's less than, just making sure you know. But anyway, you could get away without doing this. Better to do an FBD. Here's a shaft problem. It's actually very similar to the homework problem 2. This is from Schaum's outlines. I try to find as many already made problems that exist already that I don't have to invent, because that's all fraught with a lot of peril. Inventing a problem, you can make stupid things happen, or you can make the bending so much larger than the torsion that it didn't even matter that there was any torsion on there. You could have left the torsion out, that kind of thing. I try to find values. You don't care about my exam rating lows, but this problem is probably too long for an exam, but it's a practice problem, right? Here is, so a stress concentration problem with a stress concentration we have yet to use. We've not used these yet, but I tried to get clever. Another stress concentration problem with one that we have not used yet. Neither of these really needs an FBD on them. And then I have the solution. So those are what are in the solution packet. We don't have to do any of those, or we could leave them up to you. I'm not sure that my solutions are all that. These actually came out of the textbooks, those solutions. Here's my chicken scratch. Here's more of my chicken scratch. So these are all already up there, posted. So you can go ahead and look through those when you're working through them. As always, as I keep telling people, oh, look at this. Did I put this in here? Or are you supposed to see this? No. These are different exam problems I've asked over the years. So that's going to be on the video, and you can slow that down and capture it in. You don't know that I'm recycling them. I will. I don't know. Maybe. Lori says I should recycle more stuff. And I've mentioned it again twice. Yeah. So everybody take a drink. It's the drinking game of me mentioning my life. So I take requests, and as I mentioned the other day in one of my other things, don't say Freebird. It's a joke. See, there's a running joke. If there's a pause in a concert, or if they say, "Hey, what would you like to hear?" or "We're about to play one of your favorites," you gotta yell to the top of your lungs, "Freebird!" It's a running joke, and it's funny. It's always funny. Freebird. And so when somebody asks a request, and I did that one time to a friend. I was at a visit watching the band play, and the guy goes, "No charge." You don't have that on video or something. All right, you didn't need to hear that. What would we like to see? What would you like to hear? You don't care. Want me to pick something? Because I will. Because I'm in that kind of mood. It's all because of that guy, the stalker. Yeah, there we go. So, if I had a guitar, I would play something. Did I tell you? I already did. Yeah, I forgot. I've already told you everything. You shouldn't take another one of my classes because I don't have anything new to say. I'll just be reason. Have I ever mentioned? I should tell you. Okay, have I ever mentioned that I took a graduate school class? We got my master's right over here at Hartford, Rensselaer at Hartford, and my advisor, I had him for 3 classes, and that guy could never remember that he hadn't told the same story again. And so, just because I'm the way I am, I would sometimes just see the thing, and I would go, I was driving here the other day and I saw an MG. He loves MG, Morris Garage. Little tiny cars, little English cars. We'll talk about them for a half hour. So boom, there went a half hour. He had seen this movie called, not Last Night, maybe it was Last Night, and it was a King Arthur movie with Sean Connery. I can't remember. It's a terrible movie. Terrible movie. He hated this movie. He would rant on and on about it. He couldn't remember that he had already told us the same story, so I would every now and then just throw things off the rails. And so, there is something called karma, so I deserve it, so you can just go ahead and do it right back to me, because I have been that kind of student before. All right, so this really went well on the video. What would you like to do? More story time. Boom. Let's see if my orientation is right. Nope. Orientation right? Yes. I don't know if you notice, I do that all the time when I put the camera down. Yeah. Blank piece of paper. Book.
It's like a stress concentration problem.
Stress concentration problem. We could invent one. Let's take a look at the different kinds of stress concentration. Usually I work backwards in a stress concentration problem when I'm writing it so that they will land somewhere on the thing, because I've done that before on accident. So things I have not asked before. We'll do something like, this is almost too complicated. I can try to do it. No, it's too complicated. Let's do something similar to I'll go ahead and that was nasty. So this is kind of like that one problem. My imagination is not going very well. So here we go. You're going to put a load on it coming this way and a load on it coming that way. And I just won't draw the wall, but he's cantilevered onto there. And what do you think this thickness is going to be? Going to make a plate. Can you picture this plate? 0.5. This is a half-inch plate. Okay. What do you think its width is going to be? If it's by this proportion, don't you could go like, here's half, go 1, 2, 3, 4, 5. So 2.5? And what do you think this length is then? You think that's 2.5? All right, I don't give a shit. What's really important is what this distance is right there. That's the important distance, right? Because this is where it's going to be fragile. Anybody have know my fragile reference? Christmas Story, yeah. You know, they made a lot of them. They made several sequels and prequels to that. Yeah, some made from TV movies. Different actors. Never near as good. All right, so what is the distance here? All right, 1.25. Now we're going to put it, to be able to get this to be some kind of stress that we really give a shit about, we're going to have to put some serious load on here. So what do you say? I think this one needs to be bigger than that one, in my opinion. For it to matter, the axial always. We're in the U.S. units. £1,000 pounds? 2,000 pounds? 3,000 pounds. We're going to make it stupid big. 3,000 pounds. What is this damn thing? What is this? I don't know. Some kind of bracket. Somebody decided to hang something off of right here. Somehow. And then, and this one, let's make it 1,000 pounds. I have no idea if this makes any sense. Okay. So, and what is this thing made out of? What kind of steel? Or what kind of other materials? We're going to pick another material. We're going to make it brittle. We're going to make it ductile. Ductile. See, we ought to do more of this right here. This is design. We're designing. We're designers right now. You know, design starts with a D, and so does decisions. Design is all decisions. You have to make decisions. Why do you pick something? It seemed about right. That's not really a good answer, but it is an answer. I just randomly looked and saw that we were going to go 1030 cold drawn steel because we needed to pick something, and so therefore we're saying it's ductile, and so the yield strength of this thing is in U.S. units is 64 KSI. Why? Just because. All right. So we should really do a free body diagram of this, but we don't really have to. We could go like this right here. There we go. That direction and that direction. And so we'll have a reaction here. So here's our 3,000 pounds. And here's our 1,000 pounds. And so here's our reaction in the x direction, which is 3,000 pounds. And here's our reaction in the y direction of 1,000 pounds, but we'll just call it R. So this is x and y. R, y. But then we also have a moment here, so we have to have that moment, and it's right here at that section. It's inside, and that's going clockwise, so this must be going counterclockwise. So there's your moment about the z-axis. Sum of the moments about the z-axis equals 0. Boom. And so we have negative 1,000 times 1.25 plus the reaction equals 0. And I wish people in our teaching statics would do it this way right here, but they do what they want to do, which I guess is their prerogative. 1,250, I think, inch pounds. So I did loads. We should probably have done geometry first, but it's a better idea when doing have something involving a stress concentration to look up the caption, but you could probably already guess what the captions are going to say. They're going to say that the area for this guy is going to be the width minus the diameter of the hole, which we hadn't established, right? I forgot to pick a diameter. What's our diameter? Half an inch? That's really going to be, I don't know if that's proportional to this, but yeah, kind of look at that. Look at that dimension to that. Yeah, sure. Okay. So up in, you know, what we're going to need is we're going to need a d over w. D over w is going to be 0.5 over 2.5. So 0.2. That's nice. It landed on our thing. Yay. We will in a second need a ratio of our diameter and thickness. So we're actually going to need a D to H, where they're calling this H, by the way. Oh, that H. So that's going to be 0.5 to 0.5, so you're going to have 1. And, okay, so we're going to need these right up here. We go back to these captions, and so we have this situation here. We're going to have the A is W minus D times the thickness, aka H, because they decided right down here is the one that's going to be for the moment. Right, you can tell from that figure. And instead of thickness, they went H. And then for the I, so if we're looking at the geometry, we're going to have I is equal to W minus D times H, or thickness, cubed over 12. It makes kind of sense if you were to take a look at the cross section through this, which you're not really seeing right there, that you would have, the cross section that we're looking at. Here's the hole. So here's my hole right here. And then here's the axis about which this thing is bending, right there. So that A is going to be W minus D times thickness, or 2.5 minus 0.5 times 0.5. Is that going to be equal to 1? 2.5. Actually, yes, equal to 1 inches squared. And then I is going to be W minus D times H is how they wrote it, but it's thickness over 12, or BH cubed over 12, right? Where you can see that that's really, they've just subtracted out that part right there, so it's just that and that. So we go 2.5 minus 0.5 times 0.5 cubed over 12. So it's going to be a smaller number, right? 2.5. And I don't know why I keep doing that, because I could just write 2, but 0.5 and 3 raised times, and then 12 divided. And so we get, I'll write it out as decimals, 0.02833, and probably a lot more 3s. You're right, thank you. I do that. I probably made that mistake 100 times. Just from the act of looking at the thank you so much. The act of looking at the calculator and then looking back at the page, that 1 0 disappears from my brain. No excuses, just is. All right, so let's go up to, so that's like a geometry part. I guess this is sort of a geometry part too. Let me get rid of that little mouse on. So we're going to go to figure A15-1 and KT. So this is the axial one at point 2 is almost, look, that looks really close to halfway in between 2.5 and 2.6. I mean 2.4 and 2.6, so 2.5. But you could make the case it's a little bit, maybe a little bit lower than that. One tricky come on, kid. One trick I learned. Oh, I can't. I need to actually probably get really, really close up to this. Just go like that. If you're into drawing your book, but I didn't do a great job of lining my pencil up with the thickness. But what you could do now is just go like this right here. Line up where they cross. But yeah, and actually just even look at that. That looks like it crosses right there. So I think 2.5. We're okay with 2.5? I'm going to do it anyway. That's not true. I just thought it was funny to say. Are you okay with it? And then what if you would say no? After this slide. I don't know. All right, whatever, man. So I'll be a little wrong. I've been wrong before. So now we want to have this d over h is 1 and the d over w is 0.2. So let's go back to this. Look at. It was like we planned it out. There's 1 for our d over h, and then 0.2. Boom. All right. So we have now these maniacs decided to go from 1.8 to 2.2. What kind of person would do that? And leave out 2? They just jump right over 2. I don't know. It bothers me. You couldn't just put a little other lines in there? I guess not. They wanted to make it squares, and they just decided they were going to do it. All right, well, I'm questioning Joe or the people who work for Joe, probably a grad student. Actually, this is Peterson probably fault. So 0.2, damn. All right, so here's 1.8. So 2 is right in the middle of that, so right over there. It's close to 1.9. So one way that you can resolve this, if you're really, really retentive, is to grab this right in here. Boom, right to there, to there. Actually, usually do it with dividers instead of this. And then you would come up to here, and a lot of times better to like right there, and you would count out the number of segments right to there and go, ooh, an entire thing right here. All right, this is, I'm really going crazy on this, but so we really should, oh, you can't see it. There you go. So right in there is like, I can't count right now. So it's going to be like, yes, like, there's like a 6 right there, and then what you would do is you'd either go to the top or go to the bottom of this line right here and measure what those out and then get the percentage in there. We're not doing that, but I'm just going to say, I have done that before. I know, it's ridiculous. But you sit there in your office by yourself and you're like, I want to pick this thing off, and I'm like, oh, I'm getting paid by the hour. What the hell? Or the company's billing by the hour. So I'm going to say 1.88. 1.88, just to acknowledge that it doesn't look like it would be 1.9. So this is KT 1.88, and this is the bending one. There's no torsion. There is direct shear. I mean, there is a chance here, but it's never the same place as the bending. Let me see that the transverse shear, not torsional shear, it's transverse shear. Its maximum is located right here, but the bending is probably going to be right here at the top, and then compression at the bottom. So they don't happen at the same place. So even if you said you didn't say ignore transverse shear, there isn't transverse shear at the top and the bottom. There's in the middle is where it is. So they don't happen at the same place. So we can just do this in one pass here. I might call that axial, and there's a bend, and I don't leave enough room to do this whole thing. Okay, well, I'll do it anyway. Here's our KT for that one, and here's our KT for this one, and this is going to be F Y over A that we got up above, and this is going to be MC over I. So we're going to go 2.5, and here's 1.88, and the axial is 3,000 divided by 1. And then this is the moment we established was 1,250, and we're going to go 0.25 because that's C, 1/2, and then divided by our 0.020833, and 3,000 times 2.5, should be able to do it in my head, but I couldn't apparently. 7,500 PSI, 7.5 KSI. And then we have 1,250, 0.25 times, but then 1.88 times. And so we get, here's a much larger, so we didn't do a great job of, but it does matter some. We had 28,200 PSI onto the thing. Okay. And so we probably want to go maximum shear stress theory and distortion energy theory, but good knows these are already those values. Let me explain why. All right. So we will write out what the maximum stress is in the x direction. Well, this is, by the way, this is both tension and compression, but we only care about the biggest value. So it's going to be tension on the top, axial is tension. So those are the ones that we're adding together. So boom, and I'm going to make it into KSI now, 35.7 KSI. And so if we want to go maximum shear stress theory, we need to get the moment, we need, so, oh, before we do that, this is the, that's the stress element, right? Is there any stress in the y direction? No. Is there any shear? No. So more circles pretty boring. That is more circle. Now you want to do 3D more circle? There you go. Boom. Well, actually, I tell you the truth. That I think this is that. Yeah, no, this would be. No, yeah, that would be more circle. Yeah, that is more circle for that. I was just double checking. Yeah. So here is our tau abs max, which would be 1/2 or 35.70 divided by 2, 17.85 KSI. Our von Mises is boring, right? And this is completely unnecessary to do this, but it amuses me, so I'll do it anyway. $35.7 KSI, right? Square it and just square root it. Kind of pointless. It checks out. Kind of pointless. So, if we're going to go maximum shear stress theory, would be SY divided by 2 divided by abs max. So that's going to be 64 divided by 2 over 17.85. Surprise, surprise. What's that, 32? We get 1 point, whoop, nope, I got it wrong. Yeah, it should be 1 point, yeah, so, sorry, 32. I was in 1.79. And then distortion energy theory, SY divided by, it's going to be 64 divided by 35.7. Guess what? 1.79. Boring. And if you wanted to like confirm this, on a stress, a yield strength envelope, or whatever they want to call the damn thing. This point would get plotted because sigma A is equal to 35.7. Sigma B is equal to 0. As is, so this sigma 1 is equal to this, sigma 2 and sigma 3 are both equal to 0. So you'd be plotting somewhere in here. Probably something like that is where that point would be. And it would make sense that if you're drawing a line through 0, through the stress point, they'd end up, that other thing you're comparing them to is right there on the edge. So that's why they're the same. Anytime that they would land through that point, or that point, or that point, or any of the points where the that yield strength envelope where the maximum shear stress theory and the distortion energy theory share a point, you'll get the same. So that was a silly problem, but it goes through the same idea, right? Just I forgot as we were doing it. I'm like, oh yeah, no torsion, no shear. But we could do another problem that might have some more complication to it. Yes.
We have do an example. We have the envelope on it again, and then we do it and then.
I haven't decided. I don't know. I have, if I do recycle stuff, as Mrs. Steele tells me to, I might. But what type of problem? You can pick stuff out if you happen to have the book. You could just name a problem out of the book. It's often nice to pick a problem that, but we've used up a lot of the problems already. Unfortunately, there's only so many problems in there.
So how would you show the safety factor graphically
in this one right here, I would go like maybe 0, A, and then where the line crosses B right here. So I was just trying to pick it out here where this was not quite twice, because it's not quite twice the distance. Like, this right here would be 64, and this right here would be 35.7 right there, that point right there. So you would just say the safety factor on this would be OB over OA. And you should get the identical thing, except it's just how good your ruler would be. Into this distance divided by that distance. And you should get the same distance, same thing as that.
And I'm guessing x-axis would be sigma, and then y would be...
Sorry. Yeah, and so like this distance right here is SY, and that distance is SY right there.
Okay.
You're welcome. So a jerk move is to ask problems that were on exam 1, right? Ask like or that weren't on exam 1. Get a bent. Yeah, I don't want to do that. Did I ask a bent beam, a curved beam? I didn't think I did that. The strain transformation, is that what you're talking about? Superposition? Superposition. That's usually for deflection.
Yeah.
See, I can't hear you. What?
We probably maybe won't have a deflection problem.
I don't think so, because I haven't asked one before. I'm being honest. Deflection's important, but we're going to come up with some deflection coming up pretty soon. Actually, I think my next homework problem, I need to ask a homework problem soon, but it got stupid Thanksgiving. It's weird that I hate this Thanksgiving so much because I'm a professor and it just messes up our whole. I don't want to ask homework over Thanksgiving. It seems wrong. But then, like,
I know your other professors do that anyway.
Yeah.
What is even right anymore?
Was that?
What's right anymore?
I don't know. That's a good question. We take ethics into profession, but we don't take any other ethical things. I want to take a philosophy class. My PhD is technically a doctorate in philosophy. Descartes said, "I think, therefore I am." And we named the Cartesian coordinate system after him because of that. It's not true. That's not why I did it. It's not true at all. I'm a liar. So here we're, have we done this one before? We just did this one for homework, right? Have we done that one before? Have we done this one before?
Pretty similar to like the example in the notes.
Have we done this one before? Because we're going to, I think we have, right?
That one was amazing.
Have we done this one before?
No.
This is on some review things before. I have done it before. But it's way too long for an exam problem. But it is difficult. And it is extremely poorly designed.
Missing like a stress concentration in there?
We can. Let's do it. Also, we can jump ahead for stress concentration to chapter 7. And they have a real stress concentration, right? Where we have a keyway. And I got halfway through this thought and never completed it during class, it seems to me. That in chapter 7, they go ahead and give us the only information that's available they have on a keyway is in... And I did show you what Peterson's stress concentration graph, and what I was supposed to conclude was like, yeah, but if you look at this graph, there's a lot of information you just don't have. So, and I think I just ran by it. I don't know where the hell it went. It's not there. There it is. First iteration stress concentrations for a keyway. Or for other things, right? So they have this shoulder fillet. See, one of the problems when you're designing something is you don't know the diameter. You're designing for the diameter. So how do you figure out what the stress concentration is? Because you can't go diameter to diameter because you haven't calculated the diameter. That's what you're doing when you're designing. And then you haven't picked one. So this is like the first pass. And so you have a shoulder fillet. But then they give you what a end mill key seat, so like a keyway, right? So they're showing them right here, which I've never seen a keyway that looked like that, but they showed one in there, sure. So here's the only one they have. They have this end mill, and they have it for bending and torsion, and then they have a sled runner key seat, but they only have it for bending. So guess which one I use? The one where we have information for it. So here's our stress concentration for a keyway. So we'll use it because you would have that on a gear, right? You need to make sure the gear doesn't slip torsionally, and so this keyway is put in there. But the act of cutting in this little square into, the keyway for the keyway kind of looks like that right there, right? Yeah. So it has removed material. We're going to ignore that. So we're going to do it like we're just going to check the stress concentration right here at the top of that thing. We could, if we wanted to, check it down here as well. But we're going to say because it has this stress riser, we're going to treat it to right there. And you'll see that this is, and this is a first approximation, but we'll use it like all the time because we don't have a chart in Shigley that tells us what those, when we go to try to refine it, any more information than this right here. So for the keyway, here's the stress concentration in bending and torsion. 2.14 and 3 is what we'll use all the time for that. So let's go and use this terribly designed gear configuration. And pretty soon we're going to shift, we should have maybe shifted already, I don't know, to doing the design aspect of this. But we're not doing it for this exam, so I won't do it. But anyway, we'll draw to the best, it's not the best of my ability, to the quickest of my ability. I'll draw this scenario out. And that didn't look very pretty. So here you go. Here's our bearing, and continuing up here. I should use a straight edge, but if I use a straight edge, then I might get more fussy. So let's see. Here's our X, and let's see. We'll come up this way right here, and here's our dimensions close to this. So this is 9 inches, and this is 14, and this is 16, and here is our, let's see, here's straight up and down, but here is our FA equal to 300 pounds, and they are being clever by not giving us this one, FB, and they've given us the silliness. I don't like this, where they went OACB. What kind of monsters do that? I guess these guys. And then if you had this diameter, DB is 8 inches, and another great place for this one to go, DA is equal to 20 inches. And, oh yeah, this is 20 degrees. Okay, they're both 20 degrees. That's nice of them, at least. I think there's one over here that decided to go 25 degrees. I haven't even graded the recoup, have I? Oh. Yes, I know. I'll do a lot this weekend. All right, so anyway, was that?
We famous last words.
Famous last words. We will do that fast. Yeah. The leaves keep coming down. I got rid of them last weekend. That was one great accomplishment. Got rid of all of them.
And they don't, the rest of it come down.
Yeah, the rest of them. That's still a couple stragglers, so I could procrastinate. You hope it rains, then you can't do the leaves, right? It's too hard to do. All right.
My dad on the phone, he complains about the leaves right now.
It's great being a homeowner. What did I say? This is 2.14, and this was 3. Anybody remember stress concentrations? Good. Your memories aren't any better than mine. Okay, good. Excellent. Sure. One thing I didn't do yet, and I meant to, but we will eventually, is to, instead of giving you this force, tell you what the power and the RPM is. I like doing that. That's more like real world. Yeah, I like that. But we won't do it. Let's just do this problem. All right, so I'll start out with an FBD and find out this missing force. We should time how much time this takes. It could be done in this amount of time. By the way, I have seen people who have taught this class who asked this problem on an exam. And I'm like, they just didn't give a... They just didn't care. I think I kind of wish I had drawn that as a dashed line. Yeah, I didn't do a very good job with the dashed line. Because I would rather have that and that on there in terms of my FBD. That just makes it a little better for me. Ever so slightly. Because also when trying to get... that should be Z. Sorry. Z axis. Z. And this is the ZY axis. If we label that correctly. Also, just our organization helps to break it down right now instead of keep the thing going along. Z. Okay. So FAY is going to be equal to our 300 times our cosine of 20. I don't know if it's a good idea to see how fast I can go. I don't think that helps you any in terms of like being prepared for the exam. I don't know, you've done a lot of these already though, haven't you? Do you feel like you've done a lot of 3D shafts?
Probably 3 to 4.
I have had, in a kindly way, students go, no more 3D shafts! I'm like, okay, I got you. There you go. I'm so tired of 3D shafts. There's almost the Shaggy voice from Scooby-Doo. Jinkies! I used to do all these voices much better. I don't practice enough anymore. All right, so we have that set up. That was just a good thing to take care of. Now we go to the actual thing that we're here to do. Take the sum of the moments about the x direction. So we could find out this unknown FBZ. So we go clockwise with our, here I'll put the numbers in, negative 281.9, and the radius of this one is the 10 inches, or 20 divided by 2. It's going to be very fussy. And that's in the clockwise direction. This guy's in the counterclockwise direction, so we can find FBZ times our 8 divided by 2, which is 4. I know math. And so 10 times 4 divided, and we have a larger value, 704.8, call it, pounds. And from that we can find what FBY is going to be. So we're just going to take FBZ and multiply it by the tangent of that angle. 704.8 times the tangent of 20. 256.5 lbs. Sorry. And we're going to need to know the torque. So we're going to repeat the thing we just did, but now cut the shaft apart because we need to see the torque on the inside. So we have our F-A-Y, F-A-Z, F-A. And that's going clockwise, so the internal torque, internal to the shaft, must be right there. You almost want to also, I didn't put in the reactions here, but kind of should have sketched them in. So this is RZ, and but they're not. I'm not going to give them a particular one because we can't figure this out from this diagram. It's not. It can't be done. So R Y. Exactly. So the sum of the moments about the x is equal to 0, and we'll say T minus F-A-Y. Actually, I know the value, so I'm just going to put it in there instead of doing that extra step. 281.9, and then 20 over 2. So do that in your head and say you get 2,819 inch-pounds. Now we want to, I'm going to try to do it a little compact. I'd like to keep it on one page. I don't know if there's any benefit to that. I could try to do it. I tell students not to do this, so that's kind of probably Mr. Hypocrite. I mean, I could just, as I say some things, I could just see my children roll their eyes. They're tired of hearing me, when being called out for being a hypocrite, going through the same spiel about hypocrisy is a necessary part of life. All right, so you have experience with the teeter-totter. What I always think of is the teeter-totter situation where you have like this cantilevered over there. You're not quite sure what the direction of, it depends on the magnitudes of these lengths and the magnitudes of these forces. This one you can always know is going to be up. Well, no, sorry, let me put the applied forces on. Sorry, my bad. So from the side view here, which is going to be the x, y, whereas this is the x, z, coming downwards right there. From the side view here, we're going to have a force coming upwards. Here's our, I'm going to put the number in there instead of putting the symbol. And of course, I made it too close to this line right there, so I'm going to try to fix my mistake by writing diagonally up here. 281.9 pounds coming upwards right there. And then for this one, it's going to be downwards right here, and that's going to be in the y direction at B, which was right here. So here's our 256.5. 256.5. And because this is cantilevered off right here, this absolutely, I think, is necessity. Yeah, this would have to these would have to be huge in magnitude for this not to be upwards. So this is going to be our RCY. And then there's a good chance this is going to be downwards. So I'm going to go take a risk and put it in there. I might regret it. We have to watch out for our signs when we have this type of configuration because we just don't quite know. While I'm here doing this, let's go put the loads onto this side over here. And this is sort of sometimes a harder one to do because you got to look from the top down. This one again is going to be here. I'm like second guessing myself because we're looking down at this one, down this way. And so that's got this component in the z direction, so it's in the negative z direction, so that's there. This one's going to go in the positive z direction, so be down. And this value for the z direction was the 704. And then this one is the I wrote FX before on accident up here. My bad. That was supposed to be Z. And this is the 102.6. So this is like the smallest one right here. This is going to dominate the thing. So here on this side right here, we have a chance of having this reaction actually be upwards because this one is so much larger than that one. But for sure, I think this right here is going to be this direction. So here's our RCZ, written very small. And then we'll start out here bravely writing ROZ in that direction. So I shoved this over to the side so I can do all my work over here, trying to cram this stuff in there. So I take the sum of the force, sum of the moments. I'm going to do the left-hand side. So this up here is going to correspond to the side over here. Sum of the moments about O. And if I was being very particular, I would say about OZ, because it's rotating about the Z-axis at O. And go, let me write the numbers in here so I can, 16, 14, and 9. 16, 14, and 9. Right? And so this is 281.9 times 16. And plus RCY, 16 and 14 is 30. And then this one is clockwise, minus 256.5. And so it'll be 39, I think. Man, this all seems very familiar. I'm having like deja vu. There's a terrible movie called Top Secret. Val Kilmer's first movie, I think. It's a comedy. Have you ever seen Airplane? You ever seen Airplane? This is made by the same guys, but they didn't quite do it right. But they have stupid humor throughout there. But there's one of the French resistance fighters. His name is Deja Vu. And as she's leaving, she goes, "And Deja Vu, I'll always remember you." That line's pretty good. It is pretty good. Deja vu, I'll always remember you. Yeah, but it's overall, it's more cringy than funny. They tried to combine a bunch of genre movies together, and they just wasn't successful. All right, so this is negative, so I'm gonna subtract for it, but it comes out to the other side. Okay, so 30. So I got the right direction for that one. And so should we get 183.1 pounds. So check out Top Secret when you get an opportunity in your movie education. We really have filmography recently going on. Not Lost Round is funny. I told Larry about that this morning, actually. I said, yeah, I played the Raising Arizona. And she said, you just like that because John likes it. That's my best friend from high school. Is the Coen brothers? Yeah. I guess the Big Lebowski has become, although Kingpin was also no. Are we talking? Is that right? No. Am I getting somebody else confused? Am I mixing up? All right, I'm getting confused of the different brother movies, the different brother directors. Let's go back to this. Let's see. Negative ROY plus 281.9. There's some movie I have to rewatch if it's on TV. And Shawshank Redemption, absolutely. Goodfellas, have to. Godfather, have to. Oh Brother, Where Art Thou?
It's Coen Brothers.
That's the Coen Brothers? So Oh Brother, Where Art Thou is probably my favorite Coen Brothers. Really?
Yeah.
I didn't know that. How come I didn't? Did I know that? No, I don't think I knew that. Anyway, ROY. Let's double check this one. Oops. Could have put the number in this one. 183.1. I squeezed it in. It was up. Okay, good. So 281.9 atom, but then subtract that 256.3 minus. We're going to bring it over to the other side. Okay, so we got the right direction. So this one should be 208.7, unless my short attention span interfered with something in there. All right, so we got those values. I could put them into here, but let me do this first. Do the rest of here. So we're going to go some of the moments now at O about the y-axis this time. And you're going to go our 102.6 times 16. Plus RCZ times 30. And then the 704 times our 39. And I'll get RCZ 704.839 times 102.6 16 times subtract them, divide by 30, boom, get 861. That's the biggest one so far compared to those two. That's very large. I think that's going to be the dominant thing as part of our problem. I think so. Maybe. I don't think our stress concentration, actually I think this was a terrible problem, I just realized, for our stress concentration, because in order for it to matter, that needs to happen at a gear. There's no keyway at the bearing. But I can just see, because of this, I think our maximum moment is going to be right there. So it's going to ruin our plans. Ruined it. SpongeBob reference. It's all about SpongeBob when my kids were growing up. Plus 102.6 plus 861.5 minus 704.8. So you can kind of see already, right? This is going to end up being a negative result, right? So the direction that we've chosen this is, I messed up. Sorry, one second. That should be positive. These two should be negative. So I was wrong. We chose correctly. I thought I was wrong, but I was mistaken. I was wrong. So let's see. Did I do that correctly? Yes. Down is positive, as I've mentioned right there. I made that positive. This is negative, that's positive. So we should end up with a negative number. 102.6, boom, and then 704.8, and so we get 259.3 pounds. And so it's such a long, these problems are so long. 208.7, well, that's going to be 208.7. Then 281.91. Oh, I like that. Is that an alarm or is that a phone ringing? Okay. You know what I could do with that, though? Is Alan Haddad's ringtone. Because he doesn't answer it, so... And it's changed. He had this, like, dubstep thing at one point. It nearly drove me nuts. So I should add RCY to this right here at 183.1, and it should come out to 256.5. But I got 256.3, so somewhere we lost a little bit of something. 256.5, and then we should come back to 0 right here, right? Just a reminder of things to check. All right, so we this one, we're going to go negative 208.7 times 16, and we're going to get Bing down here at a negative 3,300. Did I go too far down? No. Yeah, looks like I'm on. Okay. 3339 right there. But then we're going to add to it 773.2 times 14. Boom. All right, so we do go down. All right, so we go down. Boom. To negative 2,314. And now we can double check. It should go down to 0 because there's nothing here to support it. Well, let's take a look at 256.5. That's the one we were just talking about. That's a different one, though. It's much better than the old one. You've heard it before. Yeah. Well, the one I was like last year. I'm like, there was cheers of joy when that one got changed out. Let's see, 259.3. So we can come down 259.3. And then, but not nearly enough to with the 102.6. So we're still down here in this range. 156.7, but then we're going to go upwards. RCZ of 861. So that's going to take us some serious movement. Minus, so that's going to go. Obviously, 704.8 would be correct. So that's a big one. That's not drawn to scale. Negative 704.8. That's a 4, not a 9. And so we're going to have here, boom, at 259. It's in my calculator still, so I shouldn't have to do that. Times 16, boom, 4,149. These are going to make it pretty significant. Let's see if they get overwhelmed by this other one. It's going to keep on going up though. 156.7 times 14, and we're going to add that. So no, we get a large one here. 6,343. And let's check it with this guy. So all I have to do is multiply 704 times my 9, and sure enough, we get the same thing. Pretty damn close. So yay, we're pretty confident in our statics because those work out. They don't work out to going back down to 0 at the ends. We got problems. So we want to find out our maximum. So our MA total moment is going to be 3,339 squared plus 4,149 squared and 333941. It looks like a 49. I think it's right. My handwriting is bad. So A doesn't matter. This is definitely B is going to be, excuse me, C is going to be larger than A. Because this is 5,326 inch-pounds. So MB is dominated by this guy, that's 6,000. Because that cantilever thing is sort of it's also the length of these shafts. Unless there's some machine it's attached to and you don't have any amount of control over where you place these gears, you would not make shaft lengths this long. You want to keep the different distance between the gears and the bearings short. So it's just some kind of miscommunication going on between the designers on different teams. And I was fortunate in my career often that I was taking care of a whole bunch of different systems or subsystems or things that were working with each other, so I didn't have to rely on other teams and argue with them and fight over. Especially arrangement. Arrangement is king when it comes to design. It's the first thing you do, and it's the thing that you have to keep coming back to all the time because of some kind of design reason. Somebody moves something. Yeah, and especially when it's not in your team, not in your subgroup of whatever you're designing. And so the arrangement here is what's making this whole design messed up. So we want to get the stress. So we're going to have the bending stress. It's going to be at B, and I said B, but I meant C. Sorry. They labeled the gears weird, the points weird. I don't know why B is over to the right of C, but it doesn't matter. That's what this is. So we're going to look at, this is the max right here. So we'll find the maximum stress on bending, MC over I, but we can also we could start using our 32 M pi d cubed, right? If you want to, because it's a cycle. 6752 over pi, and then we didn't say what the diameter was. 1.25 is the diameter of this. You sure I didn't assign this problem?
I think you sound like really pretty close to it.
Ah.
But
Yeah. It's very deja vu-y. And I'll always remember you. That's why I brought it up a minute ago. I will always remember. I always want to say, I'll never forget you, but it's I'll always remember you. Or I'll always think of you. I'll always remember. We have to look it up now. So this is 35.21 KSI. And then our shear stress, and we're going to actually have to probably go to another page if we want to complete this all the way, because we learned maximum shear stress theory and distortion injury theory. We could fit it into this little thing out of the side, maybe. I don't know. Now this is 16T over pi d cubed. So 16, and we found the torque to be 2,819 divided by pi and 1.25 cubed. 281916 times pi divided 1.25 cubed, boom, boom. And I say this is 7.35 35.1 KSI. And so if we're going to draw a stress element, he'd look something like that. You don't know it's a male stress element. It could be a female stress element. So just call it they. That's fine. 35.21 KSI. And 7.351 KSI. Conceding our inability to fit something onto one page. And now it's all been smushed together unnecessarily. You got no benefit out of smushing. And you've been shown to be a hypocrite. Hypocrisy. Well, do the low-hanging fruit easy. You go von Mises on this thing fast. We didn't even pick up material, so we might have to look in chapter 5. I bet they recycle these problems. They'll go, do problem 383, but find the max. They also have one that says redesign problem 383 because it stinks. They should tell you what's used for. Now, the shear isn't all nearly as much as the normal stress here. So, let's see. I'll do my calculator 3 times 1.
Where did you get the decimal?
Say again. I get up to this one. I'm sorry. So this is 37.44 KSI. And we can just plug it into an equation if we want to. I'm kind of partial to doing a more circle. Just gives me more confidence. More confidence. I hate myself for doing that. No, I don't hate me. I love me. I love me some me. There was a football player who said that. I love me some me. I think it's funny. I love me some me. Let's see. Up here, that's going to be this guy, and then if we're going to draw it kind of to scale, right to there, right? So that's this face right here is clockwise, and so that's why it's up vertically, right, up at the top part, and it's got 0 right here, so it's on that, and then down here and there. So let's see. Here's our circle drawing contest. Oh, I'm failing. I failed it. Menig. Ruined it. So why did I call it a contest? Because if multiple people are doing something, it becomes a contest. So 35.21 divided by 2, 17.61. And the radius of this one is going to be that leg squared plus this leg squared. So that leg is 17.761. And this leg is 7.351. 7 point. Why did I do that one? I don't know. Maybe 19.08. So sigma A is C plus R. 17.61, 19.08. And I've made so many videos that I have posted of these problems. And I think the people at Shigley owe me, no, I probably owe them money, huh? 6-9. I think sometimes people are searching for the answers to these problems and they're finding my videos. So I'm like the new Chegg. This would be. So that makes me a hypocrite? Seems to be a theme in this class today. Negative 1.47, that's boring. So we need to pick a material in order to assess our design. Because finding the stress, it's important, but it doesn't mean a thing unless you know what the criteria, that's plural. Did you know the criteria is plural? Criterion, when it's just one thing. No, it says criterion. I think that's true. What's that? Well, let's do brittle. Let's be brittle. Unfortunately, though, these numbers don't make it interesting at all because the B is so small. On the brittle Coulomb more, it would be seriously boring. But we could do it, sure. Let's make it the worst cast iron in the book. Terrible cast iron. My brain's no worky right now. I had it memorized at one point. I think I flipped past it, but I keep flipping. I think I flipped past it. Whee! I got a case of the dumbest. Oh, there he is, 824. All right, so we're going to say that this is going to be ASTM 20 cast iron. Gray cast iron. It's all kind of gray. Some kind of black cast iron. I guess sometimes. If it's a big old frying pan, cast iron frying pan. So this is going to fail. This is going to be terrible, actually. We should probably use a different one. That's only 22, right? See, this is already 36. That's bad design, so we're going to redesign. We're going to we already know we're going to fail. Let's go for, let's go for 40. We got a shooting chance. We got a shooting chance. Shooting chance. 42.5 KSI and ultimate 140. Cast iron likes to be squeezed. They don't like to be pulled. Give a big hug. My dog hugs. She gives good hugs. She jumps right up in my lap and stares right in my face. Like, I need to be hugged. And I think this is the equation. We're going to see soon why. I would know what this is. But anyway, what you're doing is you're comparing apples to apples, right? This is the tension one compared to the tension one. Here's the compression one compared to compression one. And a good reminder that that minus is simply there because you're comparing compression. Right? So don't actually subtract these two things from each other because this is going to be a negative value, this B right here. So you're just trying to emphasize that it's compression. So you're 1 over, and then we have 36.69 divided by 42.5 minus, and then minus 1.470 divided by 140. So you can kind of see this thing is not doing jack squat right here. Right? The compression really doesn't do a whole lot. So 36.69 and 42.5 divided. And so this has used up 86% of this capacity. Right, in this ratio says 36.69 divided by 42.5. You could think of it as using up 86.32% of the capacity. And this is only going to use up like a very small amount. So 1.47, it's going to be like 1% of the thing. Or 10%, 10%. 1%, 10%. I can't remember. 140. Yeah, it's only 1.05% of that capacity. And then you add the two things together. So you've used up, on the denominator here, 87.4% of the capacity. And then you take the inverse of it, and you get 1.14 right there as being your safety factor. It's like a different way, and having it in the denominator of thinking of this, what is safety factor? Like sort of the inverse of that, how much you used up of the capacity, the percent of it that you did. If you were to go ahead and try this on a, this is the fat one right here, fat one on that side. So here's your brittle Coulomb Moore. As I mentioned, so this is sigma A and sigma B. You're really going to be like somewhere over here. You know what I mean? And probably even that is exaggerated, that small amount, that because we're in the negative 1.47. So something like that right there, where we have crossing through the thing. Like I said, it's boring in this one. The only place that you can, what you could do is when I were to. So here's the next problem I can invent, and I have asked varying combinations of the pressure vessel with something happening to it, because I want to ask things, have things where we're using other types of stresses together, but then I can't make it too complicated because it takes too much time. So I have to be something clever. So one that I have done often, and I think there was an example somewhere in one of the homeworks, or in one of the. I don't think I did it in class. It was like one of the ones I didn't get to.
You had one where you had like a space in between it, that pressure vessel. I think at the last exam study session. You said it was something that you were kind of mean about, because you put it on, like thought about putting on during the exam in the past.
Oh, I think I've done that in a review session here. I mean, in a recitation here, where I had done. So I could pick something else right here. Well, I had one where I had a. This was an early. Actually, I think I have it in here. An early. I think I just saw it here a second ago.
I remember you doing that one.
Yeah, I'm going to do something that would be closer to what would be on an exam for this next one. Yeah, this was the ugly, evil one. So if you were, it wasn't evil. It just seemed like a good idea at the time. So I made that thing, and I'll zoom in if I can remember what's there. Exactly. So I have that thing going on right there. So I said that like somebody had made the mount for it off by an angle, and so but then they put the bolts in, and then they just cranked the holy hell out of it. So and it would make a twist onto there. So you had to go backwards from theta equals TL over JG, and then you were able to find the torque, right? So you know what theta is because you've twisted in an angle, and you know the distance, the L. So the JG, there's just the geometry and the material. So you're able to, from that TL over JG, find out what the torque was, which became an absurd amount, 487,000 inch-pounds. So that torque was a ridiculous amount. and this was homework 3, so like the third week of classes. It was in the fall. It was my first year here, fall 2017. But I thought it was an interesting problem. But let's do something a little more in the ballpark of possible. And yeah, go ahead.
So if I were to, when we calculate here on our previous example, we're going to find that in textbook. The 16.
That's a good question. Let's see if we can go and find it. These are excellent questions for exam preparation. I think it's somewhere in chapter 3, but not in an example, right? And then they start using it again, like regularly. So it will be in chapter 5 somewhere, I'm almost certain. But here you go. Here's where it was in example 3.8. Right up in there.
Do you think it'll be about the same for the 10th edition?
I think so. Yeah. These haven't changed all that much. But you might find it also in doing, the chapter that we're concentrating on is chapter 5, mostly. And in some of their examples in here. All right, so they just did that. And this is an opportunity. So here you go. Here's the torque right there. They said this. They didn't even draw a picture of it, but there you go. There's the torsional shear is the 16T over pi d cubed right there. Here's right here. They'll do it in this one, the 32M, and there's the 16T. So you'll see and this is I think this one, they're doing the problem backwards where they've left the force off of this. So we're actually trying to figure out what the maximum allowable force is going to be. Here, they did it again right here for the. So I would I think I stopped mid-sentence maybe, and I said, we do want to use this textbook. This is the book that the majority. I think it's more. I would guess more than 50% of the world mechanical engineers are taking this class using this textbook. There's a bunch of others. There are a bunch of other textbooks I have in the office. And they're all good, but I think this one's better in terms of the quality. So I'm going to invent a problem. This is danger. But try to pick out some volume. So if you were to have, so I'll make it look like a pressure vessel here. So here's a blanked flange on the end of this, right? So we got bolts holding this thing in place. And this is cantilevered off, so this pipe is coming out of a wall or something, and we're holding this thing up. And it used to be connected to some system, but now it just holds in steam or something. And let's not make it too thick, because we would like to use the thin-walled equations, because the thick-walled equations take more time. And these bolts are terribly patterned out. This is a terrible bolt pattern. And OCD is making me make that bolt right there. Okay, so these are bolted in here. And for whatever reason, somebody I'm trying to figure out what kind of torque. There's some torsion being placed on here, that torque, right? So I'm just adding in a load on here. And there's a pressure gauge right in here, and that pressure gauge is telling us that it is 600 psi. And this torque, I want to make this torque large enough that it matters, but I don't know how much that would be. Well, first off, let me see, what size pipe? Let's make it 6.5 inch OD pipe, and it has a wall thickness of 0.5. outside diameter. So its inside diameter is 5.5. But let's see, what is 6.5 divided by 2? No, we want to make this 0.25. Sorry. I want to use thin-walled equations. And so this torque, I could go ahead and say, what's the maximum torque I can put onto this thing? But that would be a jerk move to do on an exam where we haven't done it before. But I should have done it in examples and then forced you to do it on an exam. But I haven't yet, so I'm not going to.
Will the exam also only really use thin wall, not the thick wall?
You should check. Yeah. But you should check. You never know with me, right? I don't know with me. Keeping things excited. I'm going to go 2,000 and just hope that this is enough that matters or not too much. Or we could just go crazy. Let's go 6. We have a theme going with the 6s. Let's go to 6,000. Let's see what the hell happens. So here we have to do some of the assessment of our thin-walled versus thick-walled. So we'll go the RO is going to be our 6.5 divided by 2. 6.5 divided by 0.25. Why did I say divide? Oh, no, divide by 2. Oh, losing it, man. So 3.25. So our RI is going to be 0.25 minus that, right? So equal to 3 inches. And so our T over R, and we can use either one, but let's use the smaller of it, is 0.25 over 3. 0.25 over 3 is going to be 0.083333. We know that that's going to be less than 0.1, and therefore we can go thin-walled equations. I'm going to do some geometry here and find out my J. I don't need to know my I, but I do need to know my J. So that's going to be pi over 32, and we could actually go, we could look this up and we could use the radii if we wanted to, but I'm going to go ahead. I have this one memorized. So we're going to go DO squared, that's our, not squared, fourth, minus DI fourth. So pi over 32. 6.5 fourth minus 6, right? Because that'd be 2 times 3. I could do that. 6.5 for boom, 6 for boom, minus pi times 32 divide. Boom. So we get 48.01. So I'm not thinking that 6,000 isn't even large enough for me. I might want to look at that again. This 6 is pretty big. I'm going to look at it again. I don't trust myself, sorry. Minus. I get the same thing. So it seems pretty large. If you divide that by, yeah, all right. Okay, so let's get, these are the geometry. Let's get the hoop. Is going to be, there you go, I'll just draw an arrow. That's the tangential, and remember it's going to be P times DI over 2T. Is that true? Remember that? Got that memorized? 600 times 6, because that's the inside diameter, divided by 2, divided by 0.25. So how large are we talking about? That's going to be pretty good. 600 times 6, boom, divided by 2, divided by 0.25, boom. So we get 7.2 K KSI. Did I do that right?
Yeah.
Thank you. And the longitudinal will be just 1/2 of that, right? $600, 6, 2, 4. 4, sir, 4.25. So that'll be 3.600 KSI. And then we're going to have the, that was the long. Then we have the torsion. Why? Why do that? You guys haven't had me in this class. It's been doing that all semester. To randomly do that, doesn't it? It's the weirdest thing. I don't know. We have TR over J. So we have the torque of 6,000. R is to the outside fiber of 3.25. And we have our 48, which is going to make this thing much smaller than I had hoped for. But let's see what happens. 6,000, 3.25 times, 48.01 divided. Yeah, it's too small. You want to ramp up the torque so it matters? It's only 406. Well, I could have just done 36. So let's just multiply it by 6. Boom. It's still not a lot, right? 2.437 KSI. But at least it's something that matters, right? Yeah. So we do a stress element. And let's say that this is the longitudinal one, so it's 3.6 KSI. I don't have to put the KSI, but I'm going to do it anyway. And then this is the 7.2 KSI. And now this torsion, it's coming across this way. So I would say it'd be down this face right there. And these are 2.437. And we would do our Moore circle based on this. And so we would, let's see, in this top face is going to be the larger of the two, and that, but it's going counterclockwise, so it's going to be like down here. And I meant to make that right in the center, but I didn't quite do it. But we got the kind of the idea that there's going to be the center of the thing. This is this. This would be at 7.2 and negative 2.437. And I'm not going to, I guess I'll try to squeeze it in there. This is at the 3.6 and the 2.437 is the coordinates of those. And we'll draw them. Oh wow, Moore circle got real good. He did like a bump on his head. Drawing a lot of lemons today. Anyway, there you go. This is going to end up being like that. And then there's the big one. So this is the R that I'm going to use. So I find out my C is 7.200 plus 3.600 over 2. 7.2, 3.6 plus 2. So 5.4 KSI. And R square root of this value right here is going to be our 5.4 minus our 3.6. Squared. And then our, this leg right here is the 2.437 squared. So 3.6 minus, square it, and 2.437 squared plus square root. I get 3.030 KSI, and sigma A C plus R. So 5.4 and 3.03, 8.430 sigma B C minus R. I get 5.4 and minus 3.03, and I get 2.37 KSI. And so this is sigma 1, this is sigma 2, and sigma 3 is equal to 0 right there. So tau abs max is sigma 1 minus sigma 3 divided by 2. So it just ends up being 8.43 divided by 2, or 4.215 KSI, and that's located right here up above. Abs max. So if you want to try to assess this design, these are all very small numbers, but let's go ahead and pick out the weakest thing that we can find in the book. Although you probably won't, you know, most of the time, would you want to have a pretty good safety factor for a pipe like this? Because, you know, you don't know what, like, corrosion and time and loading and surges, and this is 600 psi, but what if, you know, the source of the thing has a big surge or whatever the hell? You don't want to put a pretty good amount onto there, and you don't know a bunch of other things that might happen in the future to this. So it's not out of the realm of possibility that you would want a pretty significant. But let's get like the cheapest damn steel we can get. I think there might be a table in here with cost, some type of relative cost thing. I'm trying to remember if that's true. Anyway, it's good to look at material and see how much material costs when you're trying to do a selection for the thing. So I'm going to go with the cheapest one we got right here, with the 1006. It's got a 24 yield strength of 24 KSI. I don't have anything less than that, unless we could maybe go for some exotics. I don't know if do we have anything exotic? We did have the cast iron was pretty small, right? That was the 22. That had 22 tensile strength, so that didn't want to help us out much. But we were going to go. I was going to go for distortion energy theory. Distortion energy theory. Yeah. So I don't waste your time. Let's go 24 KSI. So our yield strength is 24 KSI. And I think that was 1006 hot rolled. I think so. Yeah, 1006 hot and rolled had a 24 KSI. So, and I didn't do von Mises, so I forgot to do that. Square root of, we can't do that von Mises. Oh, so good. Yeah, here's a von Mises. So we have to do the bigger von Mises here. We have to do, so I'll write it out down below here, so we got some more room. Square root of sigma x squared minus sigma x sigma y plus sigma y squared plus 3 tau squared. So make sure that, so we're going to go back up to this. We could actually write, there's another equation we could write out. Our alternative one is to go sigma a squared minus sigma a sigma b plus sigma b squared. That was the alternative one. Because we already have the sigma a and the sigma b, but or we could do this one up here. We have a choice of either or. I'll squeeze it in there and go 7 point. Well, I guess I'll go with the way I wrote it was to be 3 point in the x one first. Squared minus 3.6. This is micro writing, sorry. 7.2. And then plus 7.2 squared. Whoops. Squared plus 3. Oh, you son of a gun. 2.473. 2.47. 2.37. 2.437 squared. See, there's a 3 right there. Can you see there's a little 3 right there? This is terrible. I'm sorry. I'm a terrible role model. Don't be like me. 3.6 squared, 3.6 times 7.2 times, but subtract it. So then go 7.2 squared and add it, and then go 2.437 squared times 3, and then add it, and then go square root, and you get 7.5, let's shoot, 30 KSI. So the safety factor, maximum shear stress theory, is SY over 2 divided by tau abs max. And we're left with 24 divided by 2 divided by 4 point, still going to be small, 4.215. So what's that? 12 divided by 4.215. So we're still left with a 2.85. But then the distortion energy theory safety factor is yield strength divided by von Mises, or 24 divided by 7.530. .19. I think it did it right. I don't know. But if we were to take a look at this, approximately, it must be showing up here somewhere, right? Because we have positive, here's positive, and here's positive, but it's going to be, this one is 3 to 4 times the size of that one. So we have like kind of this right there and that right there, so something like that. But probably, you know, I probably exaggerated the distance away from there, but you can see that, that where it crosses right here and right here is a pretty big gap. So you have a pretty big difference, fairly big difference between these two values because of where it's got, and you know that they're both positive. both of these are up in this quadrant. Right in there. So a fairly good amount of time on this. A lot of times what I'll give you I'll figure out ways to give you the J. Yeah. Or I won't ask you to, I'll ask you to the distortion energy theory, so then you don't have to do the Morse circle, because that Morse circle took us some time. I try to find ways to make this, if there's going to be 4 problems, then you would need to do math. 18.75 minute problem, which means that I have to do it in 9.37 minutes. I usually go 2 to 1 for me. And I try to go as slow as, I try to do this right here, which means it took me more than 9.3 to do this problem, so I had to reduce it somehow, reduce the amount of stuff in there. But when or I do 3 problems on an exam, 25 minutes, so that makes 12.5. I think I got close to 12.5 in this. I didn't time it. I could look back on the video. But I was also talking, so it doesn't...
It was like 2:48 when we started.
Okay. So it was like... all right, so like is it 18 minutes? Okay.
Yeah, I checked the clock.
So like 15 minutes maybe, because it was just 3 after a second ago, but now 5.
Yeah, it was 3:02.
Okay. This is a good thing to check while you're, while you're, try to, especially if you're a person that runs out of time. I know you have to get it right. You have to know what you're doing first. But I have to ask a certain amount of content, right? So there's, that's the struggle with the time. Yeah. But what's really important is deja vu. I'll always remember you.
What was it? Fluids, vibes, now this I think I remember this thing scene from this movie, actually, that advanced engineering. It was a shootout. It's weird you guys have to take that this year.
If I take it now, I'm done with my math lessons. So
Yeah.
I'll just be done.
But just like the way the curriculum is,
So it
like
doesn't come out.
mechanicals take it first semester senior year. I think you guys take it this semester.
I think a lot of us didn't start anyhow. Like either we had I had the
Ocean.
so I just
Okay.
There's no more time. We've got to take off now. I will not leave without my dog. There's no check. In a few minutes it'll be dawn, and then we'll just be sitting ducks with the aircraft down. Wait. There they are. Go. Don't worry about us. We will hear his music on the voice of America. We will hear it in the huts, the homes, and in elevators everywhere. And as long as we do, so that we are not alone. Right, Rudy. Will we get to America?
All right, we gotta get to it. Come on.
More than anything. Take me with you. Goodbye, Deja Vu. I'll always remember you.
There you go. That was worth it. Worth it. Why is it really very momsy? What's the end of this?